students, and welcome to our next topic in science. We are now in the fourth unit, and we are plowing ahead to the end of our study of life science with the following topic. This week, we are building upon last week's topic of natural selection to take it to its natural conclusion as we discuss this week the topic of evolution. So, evolution has been a controversial topic in the past, and in some circles, it remains a controversial topic even today. But we will do our best just to go over some of the basic information of evolution, and so let's dive right into it. So, if you haven't done so already, open your books to your notes page, and let's begin on the topic of evolution. I just evolved into darkness. Let me hit the right button here and we'll get into our topic of evolution. At its most basic level, to understand evolution, we can define it as a change in species over time. Last week, as we learned about natural selection and learned about the Galapagos Islands and Darwin's finches and so forth, we saw a distinct change in species over time. We studied the peppered moth last week as well, and certainly observed a change in species over time. But what makes evolution distinct from natural selection is that the species itself changes into a new species. So when we say evolution is a change in species over time, we're really talking about from one species to another. Now, obviously, this cartoon is a little oversimplification of the evolution of Homo sapien, which is simply a play on words because the human species is called Homo sapiens. And we'll get into that later on when we discuss things in class. But today, what we're going to do is we're going to begin a discussion of the different forms of evidence for or of evolution. Scientists, biologists in particular, have searched a wide field of different branches of science to come up with a list of 5 different forms of evidence for evolution. We're going to unpack these over the next couple days. Number 1 is fossil evidence. Number 2, anatomical evidence. And by the way, fossil evidence might remind you of our study last year of earth science and how we reviewed and discussed the different kinds of fossils and how fossils are formed. Anatomical evidence. In the past unit, we studied a little bit about the human body, and anatomy can apply not only to humans but to other species as well. But anatomical evidence refers to how a body is structured. Embryological evidence. Of course, we're going to unpack all of these in greater detail over the next couple of days, but you may recognize the first part of this word, embryo. And I think this year we first introduced the word embryo when we were talking about seed plants, and we dissected those beans and saw the embryo within the cotyledon of the seed. An embryo is the youngest form of an organism. Could be a plant, could be a person. Chemical evidence and molecular evidence. We'll discuss those in more detail tomorrow, and I'll explain what exactly they mean. But here are the 5 forms of evidence of evolution: fossil, anatomical, embryological, chemical, and molecular. So let's start talking about them in greater detail, beginning with fossil evidence. Some of these might look familiar to you from last year when we studied fossils. And I think we pretty much all know what a fossil is. That is, if you were paying attention to last year's lessons, you know what fossils are. But very simply, without going into a lot of detail at this time, the fossil record is the historical collection of fossils. We know from the fossil record that there are organisms that once existed on planet Earth that no longer exist today because they are extinct. And we know that because, well, we can look around planet Earth today and we don't see any large dinosaurs roaming around, for instance. And you know, other more recent extinctions like the dodo bird. We know that there are many species of organisms that no longer inhabit planet Earth. And yet, as we study and learn more about the fossil record, we are able to see how the entire spectrum of life on planet Earth has changed from one geologic period to another. In fact, if you recall from last year, these geologic eras and periods and epochs and these different time frames in geologic history oftentimes were named based on representative fossils that exist in certain rock layers. So the fossil record, very simply, is the historical collection of fossils. And of course, it's not like going to a library and checking out books on fossils and checking out every single book that was ever published on fossils. The actual fossil record in real life exists in nature. And the fossil record is continuously growing in size because we're constantly making new discoveries. We can't just literally peel back the pages of the Earth's crust and reveal them all. Many of them are discovered by accident. And as we continue to explore and discover these new regions of our planet, we uncover new fossils that perhaps we weren't even aware existed before. So the entire fossil record is always growing in size as we make new discoveries. And you might say, you could say, we will say, I'll say it right now. The fossil record is not a complete record. We will never have a complete record of all of the organisms that have existed on planet Earth. And I'll give you a quick illustration of why that is the case. On my way to school each day, I have gone back and forth thousands and thousands of times over the years, and I've seen, unfortunately, lots of dead critters on the side of the road. Whether it's a dead deer or a possum or a raccoon or a skunk or a bird or bunny or whatever the case might be, I've seen hundreds of dead animals. And many of these dead animals I've actually observed being consumed, not by people, but by other animals. Turkey vultures, for instance, love to pick apart at the carcasses of these dead animals on the sides of the road. Then I've also seen other smaller animals chewing away at the bones that remain. Without getting into too much graphic detail, you might say that I've seen dead bodies of animals completely consumed. Now, if an animal is completely assumed, is there any way possible that that animal could even begin to form a fossil? Of course, the answer is no. Because if there are no remains left because they're being digested by other species, there's no way it could even form into a fossil. So the fossil record is an incomplete record of organisms that have existed on our planet. Now, the fossil record, it does allow some important scientific discoveries and observations, analysis, and conclusions to be made. You see, as one examines the fossil record more and more over time, we are allowed an analysis of changes that have taken place on Earth over time. Because as the fossil record becomes more complete, even though it will never be entirely complete, we have seen, and by we I mean scientists who study these fossil records, we have observed that there are dramatic changes and shifts that have taken place over the course of time throughout the course of Earth history. And just think back to last year when you studied fossils and the different geologic time frames and how each of the different geologic eras and periods marked major or significant changes in the types of organisms that exist on planet Earth as indicated by the fossil record. So we can see by examining one layer of fossils above or below another just how life on Earth has in fact changed over history. Now, to help us understand this principle, I want to just reflect and remind us of a law we mentioned last year, but it ties into today's lesson in a very important way, and it is called the law of superposition. The law of superposition. And if you look at these two diagrams here, you will see that the oldest layers are on the bottom and the youngest layers are on the top. And if the law of superposition holds true, I will ask you, of these four different fossil remains that we'll label A, B, C, and D, which ones are the oldest? A, B, C, or D? It's multiple choice. Which are the oldest? Hopefully you said D. And which ones are the youngest? Hopefully you said A. Because based on how fossils that are found in sedimentary rocks are discovered, older layers are always at the bottom. So, an important point of the law of superposition is that older rocks are buried by newer ones. The youngest layers are on the top, and the oldest layers are on the bottom. Now, by looking at this, we can see, for instance, in the Grand Canyon, there are numerous different layers. The oldest layers are at the bottom, and the youngest layers are at the top. And it was through a process of erosion, which you also may remember from last year, that has cut through these layers to reveal the relative ages of these rocks. Now, this principle of the law of superposition was proposed by a scientist by the name of James Hutton. James Hutton proposed the concept of the law of superposition as he made discoveries looking at fossils in rocks, but he was more of a geologist himself, and he noted the age of rocks relative to one another were older the deeper you go. In fact, one of the important components of this law of superposition is all about what we call relative age. And this is a word I really want you to pay attention to. In fact, maybe circle this term in your notes: relative age. We are talking in this context about what is older and younger. These are relative terms. Like if you have brothers or sisters, if you've got siblings, you might refer to them as being older or younger than you. Even me with identical twin daughters, they refer to one another as the older or the younger sister, even though it's just minutes apart that separate them. But when we talk about relatives, we can talk about younger and older. When we talk about rocks, we can also talk about relative age. We don't know the exact age when we're talking in these terms. We're just talking about older or younger. So, again, if we look at this rock segment here, we can see that letter A is on the bottom and F is at the top. And if I were to ask you, well, which one of these rock layers would be the youngest, what layer would you tell me? Layer F, of course. But that's all you can tell me, that F is younger than E, D, C, B, or A. And all you can tell me is that A is older than B, C, D, E, or F. But you can't tell me exactly how old they are based solely on the law of superposition. But that brings us to the next component of age of fossils, and that is what we call radioactive dating. Radioactive dating describes the decay rate of radioactive elements. Now, what in the world does that mean? Well, here's the deal. We have discovered, and we being chemists and physicists really, scientists have discovered that there's a unique property that radioactive elements possess. It's almost as if they have a built in clock. And this built in clock measures the passage of time from hour to hour, or day to day, or year to year. And the way these radioactive elements measure time is how they decay. Now, next year in 8th grade, you're going to be learning a lot about radioactive decay, and you'll learn the specifics of how scientists can actually measure this decay. But for our purposes today, we're just going to accept the fact that different elements, whether we're talking about carbon, potassium, rubidium, or uranium, these different radioactive elements fall apart, which is what radioactive decay is all about. And they do so at a certain predictable rate, kind of like a clock. And by graphing this decay rate over time and then analyzing rocks or fossils that possess these radioactive elements, you can actually measure how old the rocks or the fossils within those rocks are. In other words, we get a better idea based on the half-life of elements, these radioactive elements, to determine what we call the absolute age of fossils. So there's another term you might want to circle: absolute age. The absolute age of fossils is a lot more specific than the relative age of fossils. As you recall, the relative age of fossils simply told us whether something is older or younger than something else. Absolute age, on the other hand, gives us a much more specific time frame, not actually an exact date of birth, so to speak, but a much more specific time frame from which the origin of the rock or the fossil came from. And how does it do that? Well, it's based on what I quickly referred to as the half life of elements, which is essentially the amount of a radioactive element that is left after a period of time called the half life. Again, next year we'll be learning a lot more details about what this radioactive decay is and how the half life is determined. It's a little bit too much for us to get into right now. So, for our purposes, radioactive dating helps to explain the absolute age, whereas the law of superposition helps determine the relative age. So please make sure you know the difference between those two types of dating methods as we prepare to go forward. Now, we spent a lot of time on the dating from the fossil evidence, and I actually have some videos for you to watch as well related to this particular topic. So I'm going to say that we will finish our notes the next time we meet and call it quits for the day here today, as far as our notes are concerned, and say to you, for now, bye bye.